So welcome back from the break. Let's do these problems. I've got a blank slide coming up on the next slide so that we can do these. So we've got 700 individuals. Question 1. So population equals 700. 85, a big A, 320, big A, little a, oops. And I think it was 295, a little a, little a. Now remember that as far as the homozygous dominant individuals are concerned, all of the alleles in these individuals are big A. So there are 85 individuals, and there are 2 of these alleles in each of the 85 individuals. So it's 2 times 85 gives us the big A's in the homozygous individuals. So 2 times 85. But then we also have to take into account that the 320 heterozygous individuals have a big A, and half of their alleles are big A. So it's going to be half of 320. Sorry, it's going to be 320. Not half of 320, it's going to be 320. We multiply 85 by 2 because each individual who is homozygous dominant has 2 alleles, so we've got to take that into account. So it's 2 times 85 plus 320. So 2 times 85 is 170 plus 320 equals 490. So there are 490 alleles that are big A, or that are big A from this population. Now, for the little a, again, for the little a individuals, the homozygous recessive, it's 2 times 295, because we've got to take into account that there are 2 alleles, plus, again, 320, because there are 320 individuals, each with a little a. So 2 times 295, I need a calculator, so let me get my cell phone. That's one calculation that I can't do in my head. Quite that good. It's going to be 295 times 2 equals 590. So that's 590. This is 170. So 590 plus 320 equals 910. Now we've got 700 individuals in the population, each carrying 2 alleles. So a gene pool equals 2 times 700, because there's 700 individuals, each with 2 alleles, which equals 1,400 alleles in total. Because remember, the gene pool is the total, the sum total of all the alleles in all the individuals. So now to calculate the frequency of those alleles, we simply divide our numbers of alleles by 1,400 multiplied by 100 to get it as a decimal. So it's going to be 490 divided by 1,400 multiplied by 100 equals 0.35. So big A, oh, sorry. Well, let's put this in the right terminology. P equals 490 divided by 1,400 multiplied by 100. Let me just do that again. 490 divided by 1400. Yeah, is 0. Well, actually, we don't multiply by 100 to get the frequency. Equals 0.35 or 35% if we multiply by 100. Q equals, what is it, 910 divided by 1400, which equals 0.65. Could have figured that out, I guess. Quick, because that is simple mental arithmetic. Equals 0.65 or 65%. So that's our answer to question 1. Question 2, just swing back to see the question. In a population at equilibrium, the frequency of little a is 0.45. What are the calculated frequencies of big A, big A, big A, little a, and little a, little a? Okay, so little a equals 0.45. And that's actually our value for Q. So big A equals 1 minus 0.45, which equals 0.55. That's our value for P. So little a, or Q squared equals 0.45 squared, which equals 0.203, rounding out the numbers. Big A, little a, or 2PQ equals 2 times 0.45 multiplied by 0.65. So 0.45 multiplied by 0.65 equals, multiplied by 2, 0.585. Move this out of the way again to see what we're doing. P squared equals, or sorry, let me do it this way, big A, which is P squared equals 0.55 squared, which equals 0.303. Now we can double check ourselves on this because the sum total of these three must be sum total 0.203 plus 0.585 plus 0.303 must add up to 1 or near to it. Remember, we rounded up, so it may not be completely accurate. So let me do the quick calculation. 0.585 plus 0.203 equals, and I get 1.091. If I hadn't rounded up, it should have added up to 1. So it's close enough. It tells me that I'm pretty close to the right numbers, even though I rounded up. This was actually 0.2025. This was 0.585. This was 0.3025. So if we do that one, I actually get 1.09. I wonder where we went wrong here somewhere. Somewhere in the math, I've made a mistake, but you get the idea of the process. Somewhere along the way. Maybe it was in my percentage. No, it is 0.35 and 0.65, so that's correct. So those numbers are correct. Yeah, the most. Oh, I'm looking at the wrong problem. Those numbers are correct. Let's see, 0.45. So that's 0.55. That's correct. 0.55, 0.45 is 0.2025. That's my mistake. That should be 0.55. I knew there had to be a problem here somewhere. So yeah, this now becomes 0.495. So if we use that, we should be a little bit closer. Yeah, these three numbers do in fact add up to 1. So double checking the calculation, we're correct. Sorry about that. Let's move on now that we've cleared that one up. As you can see, I still have issues. Math is not my strong point. I'll be the first to admit to this. I know how to use the formulas, but if I make a mistake somewhere along the way, and that was my copying mistake. I saw the 6.5 up here instead of the 5.5 over here. Anyway, moving on. So when we want to think in terms of populations evolving, in other words, allele frequencies and populations changing, there are 3 different ways in which allele frequencies can change. Natural selection is only one of them. And while natural selection is the one that we usually associate with evolution, remember evolution at its most fundamental point involves changes in allele frequencies. So if there are other ways of altering allele frequencies, there are other ways than natural selection for populations to evolve. So we do need to recognize that while natural selection is the mechanism for the Wallace-Darwin theory of evolution, and is the driving force behind adaptive evolution, there are 2 other forms of evolutionary change involving changes in allele frequency that do not necessarily have to be adaptive, and in fact, realistically are not adaptive, and they are genetic drift and gene flow. And they are distinctly different, even though it is very easy to confuse the 2. So we'll look at both of them in more detail as we go through this section. So natural selection, as you should already understand, involves differential reproductive success. Certain individuals leave behind more offspring than other individuals. They make a greater contribution to the gene pool because they have more offspring with more copies of their alleles, so they make a greater contribution to the gene pool of the next generation. And that's what natural selection is all about, differential reproductive success, measured by your contribution to the allele frequencies in the next generation. We'll talk a little bit more about how we go about measuring that a little bit later in this presentation. So that's natural selection's contribution. Genetic drift is much more difficult to understand, and it's very easy to confuse it with gene flow. But in genetic drift, there are fluctuations or changes in allele frequencies due to natural events that occur so frequently or so quickly that it is impossible for the population to adapt to it. It is a random loss of individuals from the population, not because they are selected against by environmental changes, but just because they happen to be in the wrong place at the wrong time and therefore got eliminated. And the general effect of genetic drift in its several forms is to alter genetic variation, because the survivors of a genetic drift process tend to be a random selection of individuals, not a selection of individuals on the basis of their fitness or their adaptive success. So you tend to lose genetic variation as a consequence. So here's an example of genetic drift. You've got this population of flowers, 3 different phenotypes. You have an event that occurs that eliminates a number of the red individuals, just randomly eliminates them, so that in the next population, there is only a certain number of individuals that leave behind offspring. Not everyone has an opportunity to leave behind offspring. In this case, in the second round of replication, only 2 individuals, each containing red alleles, leave behind offspring. And so the population turns out to be all red, only because these individuals were the only ones who had the opportunity to leave behind offspring. Not because they were favored, but they just happened to be the ones that left behind offspring. All the other individuals failed to do so. Perhaps there was a fire that went through and just took out all of these individuals, just randomly took them out and left behind these 2 reds. And so consequently, these are the only 2 survivors that could leave behind offspring. They are a random selection of the individuals that were there. They don't represent the original population, but they are the survivors of the population because they randomly managed to survive, and therefore they represent what the gene pool of the next group will look like. So there are 2 mechanisms that we recognize that are part of genetic drift. One is referred to as the bottleneck effect. Here, the population collapses because of some environmental thing. Could be disease, it could be famine, it could be anything, but it collapses the population in a non-adaptive fashion. In other words, the survivors don't survive because they were the best fit. They survived because they were lucky enough to survive, whatever it was that eliminated the population. And we know of several species around the world that we can point to where there have been clearly been bottlenecking effects. So cheetahs in Africa underwent a bottlenecking event somewhere around 6,000 to 7,000 years ago, because when we look at the level of heterozygosity at some of the loci in the cheetah's gene pool or genome, there is a single allele that has become fixed or locked in that position. And that's an indication that there has been a gross loss of genetic diversity at some point. And we know from the degree of heterozygosity that this was a bottlenecking effect. The population of cheetahs collapsed for some reason. Now, what may be very surprising to you is to learn that very early in the history of Homo sapiens, while we were still resident in Africa, and there was a very low population, probably less than 10,000 total Homo sapiens, our species underwent a dramatic bottlenecking effect where we think the population dropped below probably 2,000, maybe even below 1,000. And the survivors hung on along the west coast of Africa in what is now Namibia and Angola and northern South Africa. There is evidence of small populations of Homo sapiens living in caves along that coast, surviving on seafood, largely shellfish and the like, because, as best we can tell, the environment in Central Africa where we originated turned extremely hostile. There was a major environmental change, and the environment became extremely hostile, and the survivors of this event hung on along the coastline of Africa. When the environment in Central Africa returned to something that was a little bit more hospitable to Homo sapiens, the surviving population migrated back into Central Africa and expanded in population until around 80,000 to maybe 60,000 years ago, somewhere around 10,000 individuals in a number of small groups over a reasonable period of time migrated out and became the ancestors of all of us that live outside of sub-Saharan Africa. And we know that this bottlenecking effect occurred because of the limited amount of genetic variation in some loci in the human gene pool or the human genome that is shared amongst all Homo sapiens, whether we originate from sub-Saharan Africa or whether we originate from outside of sub-Saharan Africa. We know that there was a collapse in the gene pool, leading to a loss of genetic variation. And so that's the bottlenecking effect. This is the diagram that illustrates that. So the surviving population represents a random selection from the original population, and they go on if they are and survive and contribute to the gene pool of subsequent generations. And they hang on until they can evolve through mutation and sexual reproduction, a larger genetic variation in the population. If they're lucky, they will do so. Here is an example of bottlenecking that has occurred in North America, and it's affected the prairie chicken. So in Illinois, there's been a loss of habitat, which has reduced the size of the population quite dramatically, which has led to a loss of genetic variation in the genome of the surviving populations, of which there are 2 in South Central Illinois. And you can see what the effect of that has been, a loss in reproductive success. In the meantime, in 2 states where there is still a substantial level of genetic variation in the genome, the reproductive success has been quite high. This is a bottlenecking effect, again, affecting the prairie chickens, specifically in Illinois. And you can see where there's been no bottleneck. There's been very little loss of reproductive success. This is why we get very concerned about loss of habitat and why we get very concerned about isolation of populations into small populations scattered throughout what was once the range of the organism, a broader range with larger populations. This is where we see the drop in genetic diversity that leads to ultimately potential extinction or very real extinction of the species. And this is why maintaining biodiversity, maintaining habitats and maintaining high populations of individuals in those habitats is really important for the success and survival of threatened species. The other effect is called the founder effect, where a small random group of individuals becomes isolated from the parental population and establishes a new population that in a new location that they are able to survive in, and over a period of time, they accumulate their own unique set of adaptive mutations as mutations occur in this now very isolated population, and they evolve their own unique set of phenotypes and genotypes, and they become a new species ultimately. That is the ultimate extension of this. We'll talk about that in an upcoming chapter when we focus on speciation, which is really just an extension of natural selection within a population or evolution within a population. So there are a number of different examples that we can point to of the founder effect. The most famous is the Darwinian finches of the Galapagos. Each of those populations or each of those species that we see in the Galapagos must have been derived from an original small population of finches that were moved to the Galapagos almost certainly by a storm from South America. They don't represent a representative, or they didn't represent a representative selection of the gene pool of the larger population in South America. They were a random selection. Fortunately, they happened to have phenotypes that allowed them to survive in the Galapagos when they arrived there, and they were able to increase in numbers because they could thrive. But over time, they started to accumulate their own unique mutations, which allowed for the evolution of new species as they expanded their range into the many islands of the Galapagos archipelago, where they found, again, unique habitats that they adapted to, and in isolation from the other species on other islands, evolved into new species as we see them today. The gene flow can cause loss of alleles and gain of alleles. Oh, sorry, that's not gene flow, that's founder effect. We were talking about founder effect. So when a small population gets moved, I didn't realize the slide changed. So when a small population gets removed from its main population to a new location, it accumulates its own unique mutations, which means that ultimately it will become a new species if it remains isolated from the original population. Now, let's talk about gene flow. Remember, I had some real questions about gene flow as we were talking about the things that could cause a population to evolve or not. Gene flow can cause a population to evolve, or it can cause a population not to evolve, depending on the nature of the gene flow. So if there is a limited amount of gene flow, in other words, a small amount of migration, so only one or two individuals move from one population to another, that obviously has an effect on the frequency of the alleles in those two populations. The population that lost those individuals has a reduction in frequency. The population that gains those individuals has a gain in the frequency of those alleles. But gene flow can also serve to prevent evolution of a population by bringing in alleles that may have occurred in a population into a population that doesn't possess those alleles, and now introducing those alleles into that second population. So now those two populations, rather than being different from each other, tend to be more similar to each other because they contain the same set of alleles. While there was a limited amount of gene flow or no gene flow between them, they could evolve their own separate mutations. But as soon as there is a substantial amount of gene flow that brings alleles, and so long as it is reciprocal gene flow between the two populations, it tends to level out the differences and reduce the differences, so that the two populations, in terms of their gene pool, tend to be more of the same rather than different. And so those two populations remain part of the same species. That's what was happening in those fish that we were looking at that adapted to the cold water environment in Maine, but still remained part of the same species because of the gene flow between the distant populations that resulted in the cold water allele turning up in the warm water fish. That's clear evidence of gene flow between what ought to have been somewhat isolated populations, but because there was overlap between adjacent populations that allowed the genes to flow from population to population, eventually the genes turn up at the more distant populations, level things out, reduce the differences, which means the populations remain part of the same species. So gene flow is a double-edged sword. That's why I was hesitating on the previous slide, because I knew that there was that gene flow is a double-edged sword, and I wasn't really sure how I was going to explain that. But gene flow is a double-edged sword. If there is a limited amount of gene flow and it is unidirectional from one population to the other, it tends to cause the two populations to evolve, because there is a loss of alleles, and therefore a change in allele frequency when the individuals leave a population. And when they join a new population, there's another change in allele frequency because that population gains those alleles. As long as it's a limited amount of migration and it is unidirectional, it can cause populations to evolve, the two populations to evolve. If it is more reciprocal and the movement is in both directions, or there is a substantial amount of migration that tends to make sure that there are very little differences, that there is a leveling out of the differences, then it can actually prevent evolution. So here's an example where it's actually preventing evolution. So Vlieland is one of the islands that's off the northwest coast of the Netherlands in Europe. And this end of the island, let me put the pen up. This end of the island is actually adjacent to other islands down here, which are in turn are separated by a small channel from the mainland. So birds can migrate from the mainland Netherlands through those islands onto the western tip of the island, and then migrate up into these populations. And it is the frequent arrival of individuals, particularly females they've been monitoring, but individuals in general from the mainland, that is actually having an effect on the adaptation or the evolution and adaptability of this population to the environment on Vlieland versus this population. Because the central population is receiving, so the central population receives more input from migrants than eastern population. So eastern is adapting, evolving faster, and has a higher reproductive success rate. So this is the reason why gene flow can be a double-edged sword. In this case, gene flow into the central population is actually preventing it from adapting as quickly as the eastern population, which sees less input, because the migrants from the mainland tend to stop in the central population rather than moving on into the eastern population. But if individuals born in the central population migrate into the eastern population, they have greater reproductive success because they're now amongst a population that actually is better adapted to the environment because they're evolving faster. So you can see where gene flow can work in both ways. If you get substantial gene flow, which is the problem for the central population, from the mainland, it tends to level out the differences. And so the central population is not evolving and is as rapidly, and therefore is not as adapted, as well adapted to the Vleeland environment. But females that migrate from the central population to the eastern population, where there is less input from the mainland, find a population that is more highly adapted, have their own unique mutations, and as long as they can still interbreed with males from the eastern population, they can have a very high reproductive success. So gene flow can work both ways. That's why it was a little bit of a problem when we're talking about the 5 assumptions. Hopefully that clears up that. So time for another break. And we'll make this a quick one again. So how does genetic drift differ from gene flow in terms of how they occur and the implications for future genetic variation in a population? So I'll see you on the other side of the break for the answers.